Good morning, dear students. I hope you have gone through the notes of chemical equilibrium. So, the only chapter left out in order to get prepared for the fifth sem exam, it is equilibrium chapter. So, before getting into equilibrium, we need to have few knowledge, few concepts with you. That's regarding the chemical kinetic concepts. So, being a chemist, you are supposed to answer for few questions. The very first question is what happens during a chemical reaction? Answer to the question is the stoichiometry of the balanced chemical equation, or if you say the balanced chemical equation is the answer, what happens during the chemical reaction? That's fine. And the second question is, if you have written an equation, a balanced chemical equation, it looks good, it looks authentic, but still the question is, will that reaction is feasible or not with respect to the room temperature, with respect to the conditions of the nature? If you wanted to answer to this question, you need to go for thermodynamics. Thermodynamics predict whether the reaction is feasible or not. And the third question is how fast a reaction happens. The answer to the question is chemical kinetics. And the fourth question is to what extent the reaction happens. To what extent the reaction happens. Answer to this question is chemical equilibrium. So, especially in equilibrium, there is a particular parameter is what we call equilibrium constant. Equilibrium constant. Just like in thermodynamics, free energy is important. In equilibrium constant is important. So, if you look at the concepts of equilibrium constant, you have to have a prior knowledge of chemical kinetics. So, let's take a reaction. Any reaction that happens like this, a reactant will react to give a product. So, during the course of the reaction, the molar concentration of the reactants will be reducing and the molar concentration of the product will be increasing. How do you monitor the rate of the reaction? What do you mean by rate? Rate means, of course, the reactants will be consumed during the course of reaction and the products will be produced during the course of reaction. That's why product is called a product. How do you monitor the rate of the reaction? Rate means what is the speed of the reaction. So, if you take the speed of a vehicle, it's traveling from Thaliparam to Kannur, then how fast it is covering the distance. So, here the journey is from reactant to product. How fast the reactant is getting converted to product. So, if you wanted to monitor the rate of the reaction, you have two options. Either monitor the decrease in molar concentration of the reactants or by monitoring the increase in molar concentration of the product. So that could be done like this. Rate of the reaction is equal to change in molar concentration of the reactants with respect to time. Anywhere, wherever you see the term rate, that include there is an intrinsic term with respect to time, or it could be change in molar concentration of the product with respect to time. So here the molar concentration of the reactants will getting decreased, so you will have a minus sign, and here the molar concentration of the product is getting increased, so you will have a positive sign. Suppose if you go to the next step, if you take this reaction, that is N2 plus 3H2 gives 2NH3. If this is the reaction, then the rate of the reaction could be written with respect to the molar concentration of the reactants, that is change in molar concentration of nitrogen with respect to time, change in molar concentration of hydrogen with respect to time, change in molar concentration of NH3 with respect to time. So can you equate this reaction, these terms which I have written in terms of reactants and product? You cannot. The reason is the stoichiometry of this reaction and the stoichiometry of this reaction is different. So stoichiometry means here if you take 1 mole of product, you get 1 mole of reactant, you get 1 mole of product. Whereas if you take the second reaction, when 1 mole of nitrogen is getting consumed, it has to be 3 moles of hydrogen need to get consumed, and 2 moles of, as a reward, 2 moles of ammonia is getting produced. So here when 1 mole of nitrogen is consumed, equally 3 mole of hydrogen is getting consumed. So you can't equate the consumption of 1 mole of hydrogen with the consumption of 1 mole of nitrogen. So in order to sort out this issue, what we will do, we will divide the equation by stoichiometric coefficient, and here it is 1 by 2. Hope you understood. This is what the basics of chemical kinetics, and this is about expressing the rate of the reaction with respect to any of the reactant or with respect to any of the product. So there is a question, how do you express the rate of the reaction with respect to all the reactants together? So you need to look at a concept that is what we call law of mass action. Law of mass action. According to law of mass action, it says the rate of the reaction is directly proportional to the product of the molar concentration of the reactants. Suppose if there is a reaction, A plus B gives a product B. Then the rate of the reaction, rate is directly proportional to the product of molar concentration of A and molar concentration of B. Suppose if A moles of A reacts with B moles of B to give the product, then the equation will be rate is directly proportional to A raised to A and B raised to B. So when you introduce a proportionality constant, you can write R is equal to K into molar concentration of A raised to A into molar concentration of B raised to B. So you can modify the definition as the rate of the reaction is directly proportional to the product of the molar concentration of the reactants raised to the power of stoichiometric coefficients expressed by the balanced chemical equation. This is the balanced chemical equation. So R is equal to K into A raised to A into B raised to B. Please understand. This is what the law of mass action with respect to chemical kinetics. Now, if you come back to the concerned chapter, that is equilibrium, chemical equilibrium. The concept of equilibrium we have discussed in one of the previous chapter, that is phase rule. There we were discussing about a concept called vapor pressure. So in vapor, what is vapor pressure? It is the pressure exerted by the liquid molecule, it is the pressure exerted by the liquid molecule. So if you take vapor pressure, there is a closed container, comes like this. You have kept with fitted with a barometer. So there is some liquid. What will happen initially, they get evaporated, it will be here and there. So the pressure will be keep on increasing. After some time the pressure will become constant. Why the pressure is becoming constant? The movement of the molecule from liquid state to the gaseous state will happen in an extent. To the same extent the vapor molecules are getting condensed to give the liquid molecule. So the rate of the conversion of liquid molecule to the vapor molecule is exactly equal to the rate of conversion of vapor molecule to the liquid molecule at that moment. At that instant, what pressure is recorded by the barometer is what we call vapor pressure. The same happens in terms of, the same happens with respect to chemical reactions are also. Almost all the reactions are reversible. Almost all the reactions are reversible. That means a reaction, a reactant react to give product, and the product react to give back to the reactants. So what is the concept of equilibrium here in the reactants and product, if you ask? There the reactant will be reacting to give product. After some time the product will react to give back the reactants. Then at some point of time, what will happen? The conversion of the reactants to the product, to what extent happens? To the same extent product will get converted to reactants. That state is what we call equilibrium. The best reaction we have taken in order to learn about the chemical equilibrium is 2NO2 gives N2O4, or it could be even written like N2O4 gives 2NO2. The reason behind taking this particular reaction in order to learn the chemical equilibrium concept is N2O4 is colorless and this is reddish brown color. NO2 is having reddish brown color. So if you take a transparent globe and inside that if you are conducting the reaction, when the N2O4 is getting converted to NO2, the color of the mixture will be changing into reddish brown. If N2O4, the NO2 is getting reduced, it will become colorless. So by looking at the color change, you can predict the extent of the reaction. That's why this reaction is more preferred. So here you can see two graphs. In the first graph, what happened is, initially there was no NO2. There was no NO2. Only N2O4 was there. So the reaction started 0.04 mole and it was heated or something like that. The reaction happened and small amount of NO2 is produced. And here you could see that the N2O4 concentration is decreasing, NO2 concentration is increasing, and NO2 concentration increases and N2O4 concentration decreases, and after that it is becoming a straight line. What does it mean? The molar concentration of the N2O4 is not getting changed, or molar concentration of NO2 is getting changed if you take after this instant. So here you could see, after this you could see the molar concentration of N2O4 is not getting changed. It is a straight line, and NO2 is also not getting changed. It is a straight line. That means the concentration of NO2 or N2O4 is constant after this instant. So here N2O4 is decreasing, here NO2 is increasing. So it attains an equilibrium. That's what it means. So here we have taken the same reaction, but here we have taken initially NO2. NO2 is the starting reagent and the reaction started. You could see that molar concentration of NO2 is getting decreased and molar concentration of N2O4 is getting increased. After some time, see this line, it is becoming constant, where the molar concentration of N2O4 is not getting changed or the molar concentration of NO2 is getting changed. So from this you could notice that irrespective of the reactant you have taken or irrespective of the reactant, means whether it is NO2 or N2O4, it doesn't matter. The reaction proceeds in such a way that the reactants will give product and the product will react to give back the reactants, and after some time the molar concentration of the products and the molar concentration of the reactant will become constant. And here the first graph you could see that the decrease in molar concentration of N2O4 is very less, where here decrease in molar concentration of NO2 is very high. It is due to the stoichiometry of the reaction. When 1 mole of N2O4 decomposes, it gives 2 mole of NO2. That's why there is a change in the graph. So when the reaction attains equilibrium, the molar concentration of the reactants or the molar concentration of the product will become constant. So here there are two things you have to note down: which is the reactant and which is the product. How do you say? Because N2O4 gives the product, that is NO2, and it reacts back. So the product of the first reactant is the reactant in the second case. The product of the first reactant in the forward reaction is the reactant in the reverse reaction. So which is the reactant and which is the product? So IUPAC came into the scenario and told whatever you write left hand side, it will be treated as the reactants. First point. And the second point is almost all the reactants are reversible reaction. So why do you say certain reactions are irreversible? The reason is the reaction complete in such a way that the reactant will be almost converted to the products. And so that very small amount of reactant is there which is getting converted. The product will get converted to reactant. Very small. So we ignore that. So almost all the chemical reactions are reversible. There are certain irreversible reactions. The reverse reaction will be nullified. It's quite small, very, very small. So we'll come back to the same. We have discussed in terms of molar concentration. Now we will discuss in terms of the forward reaction. So if you take this reaction, the forward reaction, the rate of the forward reaction will be written as R is equal to Kf into molar concentration of N2O4. And here the rate of the reaction will be, rate of reverse reaction will be Kf, K reversed or K backward, like that we can write NO2 raised to 2, raised to the power of stoichiometry coefficient. So here we have taken N2O4 as the reactant. So the decrease in molar concentration is reflected in the rate of the reaction, because as the molar concentration of the reactant decreases, the rate of the reaction also decreases. So that's what you have seen over here. The rate of the reaction is decreased. The same time, as the molar concentration of the NO2 increases, that's the product over here, the rate of the reaction also increases. So you could notice that the rate of the reaction, the forward reaction is decreasing because of the molar concentration of the reactant is decreasing. Both the molar concentration of the reactant and the rate of the forward reaction, both are getting decreased, keep decreasing. The same time, the molar concentration of the product is increasing and the rate of the backward reaction is increasing, and rate of forward reaction decreases and the rate of forward reaction increases. It reaches to a particular point where the rate of forward reaction is exactly equal to the rate of backward reaction, and this state is even, again we call it as chemical equilibrium. Chemical equilibrium. So now we can have a question, what is chemical equilibrium? So you can have a definition for that. It is the state of reversible reaction where the molar concentration of the reactants and the products is constant, or the rate of the forward reaction is exactly equal to the rate of backward reaction. So it's a state of the reversible reaction. And one more thing, you should understand, it is called as dynamic equilibrium. The reason is the molar concentration of the reaction and product is constant, not because the reaction is not happening. It is because the rate of forward reaction is exactly equal to the rate of backward reaction. So initially I have told you, chemical equilibrium we learn to predict the extent of the reaction, to what extent the reactant got converted to product. So how do you represent it? By using a scientific term. For that only we have equilibrium constant. Equilibrium constant. So what is equilibrium constant? Let us take a reaction. A moles of A reacts with B moles of B to give C moles of C and D moles of D. This is a reversible reaction. So we have learned about equilibrium. At equilibrium, the rate of forward reaction is exactly equal to rate of backward reaction. Rate of forward reaction is exactly equal to the rate of backward reaction. So we can write down the law of mass action expression for the rate of forward reaction as well as the rate of backward reaction. So RF is equal to KF into molar concentration of A raised to A into molar concentration of B raised to B, and RB backward reaction is equal to Kb into molar concentration of C raised to C into molar concentration of D raised to D. Okay. So if you equate both the equation, because according to this condition Rf is equal to Rb, even you can write on Kf into molar concentration of A raised to A into molar concentration of B raised to B is equal to Kb into molar concentration of C raised to C into molar concentration of D raised to D. So if you rearrange this equation, you can write down Kf by Kb, here it is small letters, is equal to C into C raised to C into D raised to D divided by A raised to A into B raised to B. So we are connecting the rate with respect to the concentration. So here the ratio of the rate constant, this Kf I didn't mention, actually this Kf is what we call rate constant. You have learned from chemical kinetics. Rate constant, what is the significance of rate constant? How fast the reaction is. If the rate constant value is very high, that means it is quite faster. If it is quite small, it is very slow. That's what it means. So if the rate of forward reaction is very fast and the rate of backward reaction is very slow, then this parameter will be very high. It is a large value, high value. So we'll not go into that direction now. So if you if you can predict the ratio of the rate constant of the forward reaction to the rate constant of backward reaction, that will give you an idea about what amount of the concentration of the reactant or product will be more in the reaction mixture. So this is very important, and this value is, that means the ratio of the rate constant of forward reaction to the rate constant of backward reaction is represented by a parameter that is capital letter K, is what we call equilibrium constant, is what we call equilibrium constant. This is what the equilibrium constant, and this what is there here, this is an expression, we call it as equilibrium expression. Equilibrium expression. And one more thing to keep in mind, you can write down the same expression in a simplest way, that is equilibrium constant of a reversible reaction is the ratio of the molar concentration of the products to the molar concentration of the reactants. Ratio of the molar concentration of the product to the molar concentration of the reactants. If at all you are taking the reaction as a reactant gives P. So please understand. So let's discuss the rest of the part in the next class. Please go through the video once or twice or thrice until you understand. This is very fundamental, and you have to understand these part, then only you can switch over to the next part. Thank you.